Welcome back to the deep dive. We grab those dense source materials, the ones that are tough to get through, and we boil them down, give you the essentials so you're quickly up to speed.
Right. And today we're diving into predictive analytics, specifically a really foundational but super powerful area, tree-based methods.
Yeah, these are the models that kind of work by splitting up your data, right? They drive some really important predictions, think finance, medicine, all over.
Exactly. And our goal today, our mission, if you like, is to trace how these things evolved.
We'll start with the basic building block, the decision tree, pretty straightforward. Then we'll see how modern machine learning takes that simple idea and builds these real powerhouses like bagging, random forests, boosting.
And even newer stuff like BART, which is a kind of hybrid model.
Okay, so let's start at the beginning. What's the fundamental idea behind any tree-based method?
Well, the core concept is actually pretty simple on the surface. These methods work by partitioning or segmenting your predictor space. Basically, they chop up your input data into a set of simple, distinct regions.
And these regions get organized into that classic tree structure, like a flowchart.
Precisely. It looks just like a flowchart, making it easy to follow the logic.
And that structure, that visual aspect, immediately brings up this big trade-off you always see in modeling, doesn't it?
It really does. A single decision tree on its own is incredibly interpretable.
You can draw it out. You can literally point to the path and say, okay, this is why the model made that prediction. You could probably explain it to a non-expert pretty easily.
That transparency is a huge plus. Huge. But the flip side, the con, is that single trees, they often just don't have the predictive muscle. They tend to have high variance, meaning they can be unstable, and their accuracy often isn't state-of-the-art compared to other methods.
Right, which explains why the real action, the real progress in tree methods isn't about making one perfect tree. It's about combining them.
Exactly. It's about ensemble methods combining hundreds, maybe thousands of trees. We use techniques like bagging, random forests, and boosting to aggregate all these trees.
And that aggregation dramatically boosts the accuracy.
It does.
Yeah.
But, and this is the trade-off, you lose some of that beautiful interpretability. The final model becomes more of a bit of a black box.
Okay, let's peel back the layers then. Let's start with that single decision tree. How does it actually decide where to draw those lines, make those splits in the data?
So it uses an approach the sources call top-down greedy. It's technically known as recursive binary splitting.
Top-down, meaning it starts with all the data.
Yep, starts with everything at the root node, the top of the tree. Then, step by step, it looks for the best possible way to split the data into two distinct, non-overlapping groups.
And greedy. What does that mean in this context? Is it just grabbing the best split it sees right now?
That's exactly it. It's short-sighted in a way. At each specific step, it picks the one split, the predictor, and the value to split on that gives the biggest immediate improvement in reducing the error.
So for regression, where you're predicting a number, it's trying to cut down the residual sum of squares, the RSS, as much as possible at that single step.
Correct. It maximizes the immediate RSS reduction. It doesn't look ahead, 2 or 3 splits down the line to see if maybe a slightly less good split now might lead to a much better overall tree later. It just takes the best gain right now.
Okay, let's make that concrete. The sources often use that baseball salary example, predicting a player's salary using things like years played and number of hits.
Right, that's a classic. And if you actually plotted that data, you'd likely see some patterns. The tree algorithm tends to find them. The first split it typically makes, the most important one, is usually on years of experience. It might draw a line around, say, 4.5 years.
So players with less than 4.5 years go one way into maybe a lower salary prediction?
Exactly. They form one branch, one region. And players with 4.5 years or more go down the other branch towards potentially higher salaries.
Okay, so that first split tells us years is a big deal overall. But what about that group with more experience? They're probably still pretty different from each other.
They are. That group isn't homogeneous yet. So the algorithm looks only at those players, the ones with 4.5 years, and makes another split. This time, maybe it uses hits. It could split them based on whether they have, say, fewer than 117.5 hits or more.
So now you've got 3 distinct groups, 3 leaves on the tree, low experience, high experience but low hits, and high experience with high hits.
Precisely. And each leaf corresponds to a predicted salary level, lowest, medium, highest. It's a very neat stratification based on the data.
And that 3-leaf tree is super easy to understand, but what if we just let the tree keep splitting, keep going until every player is in their own little leaf node?
Well, you'd get a tree that perfectly predicts the salary for every single player in the training data.
But it would be useless on new data, right? It would have just memorized the noise. Overfitting.
Exactly. Massive overfitting. So the standard strategy is actually a bit counterintuitive. You first grow a really big, complex tree, maybe deliberately overfit it a bit.
And then you cut it back.
Yeah. Then you prune it back using a technique called cost complexity pruning, sometimes called weakest link pruning.
How does that work? Like, how do you decide where to prune?
You introduce a tuning parameter, let's call it alpha. Think of it as a penalty for complexity. Each terminal node, each leaf, adds to this penalty. So you essentially consider a whole sequence of trees, from the biggest one down to just the root node, each corresponding to a different value of this alpha penalty.
And how do you pick the best alpha, the best level of pruning?
Cross-validation. Standard k-fold cross-validation. You try out different values of alpha, calculate the error for the pruned tree corresponding to each alpha on the validation folds, and pick the alpha that gives you the lowest average error. That's your optimally pruned tree.
Makes sense. Now, what about classification trees, where you're predicting a category like cancer versus no cancer, not a number like salary?
A very similar structure, very similar process, recursive binary splitting again. But the goal isn't to reduce RSS anymore, because RSS doesn't make sense for categories.
Right, so instead of predicting the average value in a leaf node,
You predict the most common class in that leaf node. If a leaf ends up with 8 cancer patients and 2 no cancer patients, the prediction for anyone landing in that leaf is cancer.
and the splitting criterion changes too, right? You can't use RSS.
Correct. You need a measure of how pure a node is. Does it contain mostly one class, or is it a big mix?
Is that where things like the Gini index come in?
Exactly. The most common criteria are the Gini index and deviance, which is related to cross-entropy.
Why not just use the simple classification error rate, the fraction of misclassified points in a node?
You could, but it turns out Gini and deviance are much more sensitive, especially for growing the tree. The error rate might not change much for a potential split, even if that split makes the resulting nodes significantly purer.
Ah, okay. So Gini or deviance give the algorithm a better signal to find the really useful splits early on.
Precisely. They measure impurity better, so they guide the tree growing process more effectively than just counting errors at each node.
Okay, so we have these single trees. Interpretable, but maybe not super accurate. This brings us back to the main challenge.
Right. How do we get the best of both worlds? Or at least how do we seriously boost the accuracy, even if we sacrifice some of that crystal clear interpretability?
And the answer is combining them. Ensembles.
Ensembles. And the first major ensemble technique is bagging. Stands for bootstrap aggregation.
Bootstrap aggregation sounds fancy, but the underlying idea is pretty fundamental in statistics, isn't it? Averaging reduces variance.
That's the core principle. If you have multiple independent measurements or predictions of the same thing, averaging them usually gives you a more stable, less variable estimate.
But we usually only have one data set, so how do we get multiple predictions to average?
That's where the bootstrap part comes in. We simulate having multiple data sets by bootstrapping our original one. We take repeated random samples with replacement from our training data. Say we have n observations. We draw n observations with replacement to create a new bootstrap data set.
Right.
We do this b times, maybe a few hundred times.
With replacement is key there, right? Means some data points might get picked multiple times in one bootstrap sample, and some might not get picked at all.
Exactly. So each bootstrap dataset is slightly different from the original and from the others. Then you grow a full decision tree, usually unpruned, deep trees work well here, on each of these B bootstrap datasets.
And then to make a final prediction.
For regression, you just average the predictions from all B trees, simple average. For classification, you take a majority vote, whichever class gets predicted most often across the B trees wins.
Okay, that makes sense. You get lots of slightly different trees, and averaging or voting cancels out some of the noise and instability of any single tree.
Precisely. It reduces the variance. Now, there's a really neat side effect of that sampling with replacement in bootstrapping.
What's that?
On average, for any given bootstrap sample, about 1/3 of the original observations won't be included because we're sampling with replacement.
Oh, right. They get left out of that particular sample.
These are called the out-of-bag, or OOB, observations for that specific tree. You can use them.
How? As like a built-in test set for that tree.
Exactly. For tree number B, you take all the observations that were OOB for that tree, run them through tree B, and calculate its prediction error only on those OOB points.
And then you average that OOB error across all B trees.
Yep. That gives you a single reliable estimate of the model's test error, the OOB error estimate. It's calculated internally during training. No need for a separate validation set or cross-validation sometimes. If B is large enough, it converges to what leave one out cross-validation would give you. Pretty cool.
That is cool, free error estimation. But bagging still has a potential weakness, doesn't it? What if one or two predictors are just really, really dominant?
That's the issue. If you have, say, one predictor that's much stronger than all the others, like our years predictor in the baseball example,
Then pretty much every bootstrap sample will still feature that predictor heavily, and the top splits of most of the bagged trees will probably use that same predictor.
right? Which means all your B trees end up looking quite similar. They become correlated.
And if you average variables that are highly correlated.
You don't get nearly as much variance reduction as when you average independent or less correlated variables. That correlation limits how much bagging can actually improve things.
Which leads us perfectly to the next big innovation, random forests. They directly attack that correlation problem.
They do. Random forests are an enhancement of bagging designed specifically to decorrelate the trees.
How do they do it? What's the tweak?
It's actually a pretty simple but brilliant modification. When building each individual tree in the forest at every single split point, the algorithm doesn't even consider all the available predictors. Instead, it randomly selects a small subset of the predictors. Let's say there are P total predictors. Maybe it only considers M predictors, where M is much smaller than P.
So it's like, okay, time to make a split. It randomly grabs, say, 5 predictors out of maybe 50 total, and it only looks for the best split among those 5.
Exactly. It finds the best split only within that random subset.
Even if the globally best predictor wasn't in that random subset.
Even then, it's forced to find the best split using only the predictors it was randomly given access to at that node.
I see. So even if years is the super dominant predictor, if it doesn't happen to be in the random subset chosen for a particular split, the tree is forced to use something else, hits or assists or whatever is in the subset.
Right. And this happens independently at every split in every tree. This forces the trees to be much more different from each other. They can't all rely on the same 1 or 2 strong predictors for all their important splits.
They become less correlated, decorrelated.
That's the key. That randomization injects diversity, reduces the correlation between the trees in the forest.
And when you average these less correlated trees,
You get a much more significant reduction in variance compared to standard bagging. This typically leads to a substantial improvement in predictive accuracy.
what's a typical value for that subset size?
A common rule of thumb is 1 approx score classification and maybe 1 approx P335 for regression, where P is the total number of predictors. But it's a tuning parameter you can optimize.
Okay, so random forests build on bagging by adding that predictor randomization at each split. Both bagging and random forests build their trees sort of independently, in parallel, right?
Correct. Each tree is grown largely independently of the others, using bootstrap samples and maybe predictor subsetting, that you just combine them at the end.
Which brings us to boosting. And boosting is different. It's sequential.
Completely different philosophy.
Yeah.
Yes, boosting is inherently sequential. It doesn't build trees independently in parallel. It builds them one after another, and each new tree explicitly tries to fix the mistakes made by the trees that came before it.
Fix the mistakes. How does that work?
It focuses on the residuals. After you build the first tree, or the first few, you look at the errors. It makes the difference between the actual values and the predicted values. These are the residuals. The next tree isn't fit to the original outcome variable. It's fit specifically to those residuals from the current model.
Ah, so it's trying to predict the leftover error.
Exactly. It's trying to capture the part of the signal that the existing ensemble hasn't yet figured out. Then you add this new tree into the ensemble, update the residuals again, and fit the next tree to the new residuals, and so on.
It sounds like it's learning slowly, piece by piece.
That's a key aspect. Boosting algorithms are designed to learn slowly. Each new tree added only makes a small incremental improvement to the overall model.
How is that slow learning controlled?
Usually by a parameter called the shrinkage parameter, often denoted by lambda. It's typically a small number, like 0.01 or even 0.001.
And what does shrinkage do?
It scales down the contribution of each new tree before adding it to the ensemble. So instead of adding the full tree fit to the residuals, you only add a tiny fraction, lambda times the tree of it.
Why do that? Why learn so slowly?
It helps prevent overfitting. By taking lots and lots of very small steps, allowing many trees to contribute just a little bit, the model becomes much more robust and less likely to latch on to noise in the data compared to taking a few large, aggressive steps.
Okay, so slow learning via shrinkage is important. What other knobs do we need to tune for boosting?
There are generally three key tuning parameters. First is the number of trees. B. Unlike bagging in random forests, where more trees is usually better, or at least doesn't hurt much after a point, boosting can overfit if B is too large.
So you absolutely need cross-validation to find the optimal number of trees for boosting.
Absolutely essential. You monitor the error on a validation set as you add more trees and stop when the error starts to increase.
Okay, number of trees, B. Second is the shrinkage rate we just discussed.
Right, that controls the learning rate. Smaller lambda generally requires a larger B.
And the third?
The complexity of each individual tree. Often this is controlled by limiting the interaction depth or the number of splits. Let's call it D.
So how complex is each tree that's being added sequentially?
Exactly. And interestingly, boosting often works remarkably well with very simple base learners trees with only a few splits, or sometimes even just one split.
A tree with only one split, that's called a V.
A stump.
Yeah.
A decision stump. AdaBoost, one of the earliest popular boosting algorithms, often used stumps. More modern methods like gradient boosting machines, GBM, often use slightly deeper trees, maybe D4 or D6, but still relatively small compared to the deep trees in bagging or random forests.
And how does boosting perform compared to, say, random forests?
It's often very competitive, sometimes even slightly better, especially with careful tuning. The sources mention an example with high-dimensional gene expression data predicting cancer type with like 500 predictors.
What do they find there?
Boosting slightly edged out random forests in terms of error rate. But crucially, both were massively better than a single classification tree, which apparently had an error rate close to 46%, basically useless. Boosting in random forests got the error way down.
Wow, that really highlights the power of ensembles. Now, with random forests, you mentioned we could still get a measure of variable importance, even though the model is complex. Can we do that for boosting too?
Yes, you can get variable importance measures from boosted models as well, often using similar ideas.
How did it work for random forests again? Summing up the error reduction.
Yeah, for random forests or bagging, a common way is to look at a specific predictor, say years. Every time years is used for a split in any of the B trees, you measure how much that split improved the node purity, like reducing the Gini index for classification or RSS for regression. Then you sum up all those improvements across all splits involving years in all the trees and average it. Predictors that consistently lead to large improvements are deemed more important. Similar logic can be applied in boosting contexts too.
So even if the model is a black box, you can still peek inside and see which inputs drove the predictions.
Absolutely. Variable importance is a really valuable output from these ensemble methods.
Okay, we've gone from single trees to parallel ensembles like random forests, then to sequential ensembles like boosting. Where does that leave us now? Is there anything beyond boosting?
Well, one interesting development that kind of blends ideas from both worlds is BART-Bayesian additive regression trees.
BART. Okay, Bayesian. That sounds different. How does it fit in?
It's definitely an ensemble method, and it relates to both bagging RF and boosting.
How so?
Like bagging in random forests, it typically involves maintaining a sum of many trees, maybe K trees, often shallow ones.
Okay, sum of trees, like an additive model.
Right. But like boosting, the way these trees are constructed or modified often involves looking at what the rest of the model isn't explaining yet. It implicitly considers the residuals.
So it's got elements of both parallel structure and sequential learning.
Kind of. But the real novelty in BART, driven by its Bayesian foundation, is how the trees are updated. It doesn't typically involve completely refitting trees based on residuals in the same way as gradient boosting.
What does it do instead?
It uses a process based on Markov chain Monte Carlo, MCMC. It iteratively proposes small, random perturbations to the current set of trees.
Perturbations? Like what?
Things like randomly picking a tree and proposing to grow it by adding a new split, randomly picking a node and proposing to prune its children away, or just changing the predicted value slightly in a terminal node.
And these proposals are accepted or rejected based on Bayesian rules.
Exactly, based on whether the proposed change improves the model's fit to the data, while also incorporating prior beliefs about model complexity, which helps regularize and prevent overfitting. It's a stochastic search through the space of possible tree ensembles.
That sounds computationally intensive, maybe, but potentially very robust.
It can be intensive, yes, but the Bayesian framework naturally guards against overfitting. Because it's not aggressively fitting residuals like standard boosting can, BART often performs extremely well right out of the box with minimal tuning.
That's a big plus. Less fiddling with parameters.
Huge practical advantage. And another major benefit comes directly from the Bayesian approach. BART doesn't just give you a single-point prediction.
What does it give you then?
Because it runs this MCMC process, it generates samples from the posterior distribution of the model. You end up with not one final model, but a whole collection, like thousands of plausible tree ensembles that fit the data well.
And you can use that collection.
To get a point prediction, you typically average the predictions across all those sampled models. But crucially, the spread or variation in the predictions across those thousands of models gives you a direct, built-in measure of uncertainty about your prediction.
So you get confidence intervals essentially for free.
Pretty much. You get a credible interval directly from the posterior samples. You know not just the likely prediction, but also how confident the model is in that prediction. That's incredibly valuable in practice. High accuracy, often low tuning effort, and quantified uncertainty. BART is a very compelling package.
Okay, so let's try and wrap this up. We've journeyed quite a way. We started with a simple decision tree, easy to understand, segmenting the world into rules.
Very interpretable, but often not the most accurate.
Then we moved to ensembles, bagging, averaging, bootstrap trees, random forests, adding that clever predictor randomization to decorrelate them.
Boosting learning sequentially, focusing on errors, using shrinkage.
And finally, BART, the sort of Bayesian hybrid that updates trees through perturbations and gives us uncertainty estimates.
And these ensemble methods, random forests, boosting variants like GBM or XGBoost, and BART, they really are among the workhorses, the state-of-the-art for many supervised learning tasks today, especially with tabular data.
Why have they remained so relevant and powerful?
A big part is their flexibility. They naturally handle nonlinear relationships between predictors and the outcome. They don't really care if the effect of hits changes depending on years.
And they handle different types of predictors easily too, right? Numbers, categories.
Effortlessly. You don't need to create dummy variables for categorical predictors like you do for linear models or neural networks. Trees just handle them naturally with splits. That simplifies the whole data preparation pipeline quite a bit.
Okay, so they're powerful, flexible, relatively easy to use, especially random forests and BART out of the box. But let's end on a more provocative thought. You mentioned earlier how those simple single decision trees, the ones we started with, arguably mirror how humans sometimes make decisions. We use simple rules, thresholds.
Yeah, there's definitely an intuitive appeal there. If experience is low, predict low salary. If experience is high, ND hits are high, predict high salary. It feels cognitively plausible, maybe?
Yet, the methods that give us the best predictive accuracy, the random forests, the boosted trees, BART, they're these complex aggregates of hundreds or thousands of trees. They're opaque. No single human could really hold that entire model in their head and explain why it made a specific prediction in simple terms.
It's true. The gain in accuracy comes at the cost of that direct interpretability.
So what does that gap tell us? This difference between the models that resemble our own apparent decision strategies and the complex aggregated models that actually perform better. Does it say something about the limitations of our own unaided human decision-making?
It's a fascinating question, isn't it? Is peak predictive power inherently complex and to some extent uninterpretable by a single mind? Does achieving that accuracy require moving beyond simple intuitive rules?
Is the price of optimal prediction always a loss of transparency? Maybe not just for machines, but maybe even hinting at limits in our own cognition. Something to chew on.
Definitely something to think about.